Hello, Physics Nation. My name is Nate Larmond, and I'd like to set up an experiment called launching marbles. So we used our little CPO marble launcher, fired vertically, and measured the hang time. So start, stop. How long does it take a projectile to go up and down? In a previous lab, we actually measured our body's hang time. How long can you jump off the floor? And we did kinematics. We did basically projectile motion. So you cut the total time in half. That's called the apex time. You assume the acceleration to be negative 9.8 meters per second squared. Acceleration multiplied by the apex time will tell you how fast you're going when you leave the ground. Then you assume that you stop at the top. So right in between your launch velocity and the apex, you can find the average velocity. You just take your launch velocity and divide by 2. If you know average velocity and the time it takes to stop, you can actually predict your vertical leap. If average velocity equals displacement over time, then displacement equals average velocity multiplied by apex time. And you're supposed to slap tape on the wall and actually measure your vertical leap. I think I was the only one that actually slapped tape on the wall, but that's okay. It's never too late to directly measure your vertical leap. So kinematics was an old lab. Now, find a Nerf gun. They're cheap at the Goodwill or Salvation Army or whatever. You don't need the fancy $100 marble gun. Honestly, you could just drop a tennis ball, measure its hang time after it strikes the ground if you wanted a really consistent impact. Golf balls are also sort of magical. They're super cheap at Goodwill or Salvo. Make it happen at home. There is nothing that can replace real experimental data because there's uncertainty, and that's really the theme of this lab. We all observe the same event. Start, stop. We should all get the same time, and yet we did not. So here's a typical set. I fired the marble gun at setting 4. That is a pretty big hang time. It almost hit the ceiling. 1.5 seconds to go up and come down. So we've done average many, many times. Equal average, hang on, let me make this real big. Equals average, open parentheses, click and drag through the set you want to find the average for. In this case, it's cells D4 to D10, close parentheses, and there you go. Our new trick is standard deviation. Let me make this one real big. So equals STDEV, open parentheses, click and drag through the set you want to find the standard deviation for, and then close parentheses. Getting the number is important. Understanding what the number means is much more important. If you are deviant, you are far from average. I say I eat mayonnaise for breakfast. I just scoop it right out of the jar because I'm odd, I'm weird, I'm deviant. That is far from the middle. Standard deviation just means the typical distance of a measurement from the middle of the set. So we bounced around 1.5 seconds by a typical amount of 0.15 of a second. So most of our measurements were 1 standard deviation above or 1 standard deviation below. 1.5 seconds plus 0.15 of a second would be 0.65 seconds. And then 1.5 seconds subtract 0.15 of a second would be 1.45. So most of the measurements lay within that range, in between 1 standard deviation above and below, in between 0.65 and 1.65 and 1.45. I think it's like 68% of the data that is normally distributed is plus or minus a standard deviation. But I'm no statistics expert. Consult a math teacher on that one. Anyway, the game we're going to play is to shoot the marble not at setting 4, but at setting 3, 2, 1. So we get less and less hang time. The first one was 1.5 seconds, and then not so much, and then itty-bitty hang time. Will we become more precise? Less precise? Will the range get more sloppy, more tight? We don't know, okay? So a student suggested, let's do a branch-off experiment. Let's do a variation of the official, my experiment. Once you learn how to ask your own questions and seek the truth, you don't need your teachers anymore. So that's really why we come to science class, to sort of brainstorm interesting new questions. And this student did have an interesting new question. He said, well, the online students who are looking at this marble have a big disadvantage. The webcam may glitch, the Wi-Fi may glitch out, and so they're really just listening to the event. But is that an advantage or a disadvantage? Are they, I don't know. So this is sort of the extension exercise. You can take this raw set of data and you can filter out which students are online and which students are in room 404 with a simple if statement. So let me make this guy real big. If statements are simple. So equals if, open parentheses, B4, hang on, it's kind of messed up. Whoa. Equals if, open parentheses, B4 equals online, that is, if it's in quotations, it's text. If this cell location has the text online, then enter into this cell whatever is in D4. See the little purple highlights? That's D4. All right, so you're saying if this logical expression is true, do this. Enter the value that is in D4. And if it is not true, do this, that is, enter a blank. So that's how logical expressions work in Sheets, or one of them anyway. If is a very powerful filter. You can look at this cell in yellow, and if there's a particular text there online, enter what is in D4. If that particular text is not there, enter a blank. And then you just fill it on down. And so you can pull out, see how it lines up with the online pieces of data? You can pull out a set. And over here, same basic idea, except, let me make this one big. Except now we're not looking for the text online, we're looking for the number 404. So if the value of B6 is 404, enter D6. And if the value of B6 is not 404, well, then just enter a blank. So this is our first logical expression in Sheets. Thanks for watching. See you in the next video.